So resonance, we are talking about factors that influences mechanism of reactions and how to go about the reaction process in organic compounds or in organic reactions. So I said if you want to do resonance, you have to know level structure, how to write level structures and formal charge. So I have to do this I have to simplify this and shift this one in because I will have just go to resonance and begin to write the structure and movement of arrows. But if you know this will be a guide so that you don't make mistakes in writing resonance. What is resonance? Resonance is just like localization of pi electron system. So the localization of pi electron system of electrons, or let's say pi electrons, right, within a system of organic compound. Within a system of organic compounds. So what do I mean by this? For example, look at this compound this way. Alright. So it has a lone pair here. I can move this one and make it have what we call an hybrid. Sorry. So I've moved this one of the bonds. So I've moved it to turn to what? Lone pair. So we will carry minus and this one will carry plus. Now you are starting with neutral atom or neutral compound here. What are you ending with? Neutral compound. Because you know that negative plus positive will give you what? Neutral. So I just want to get the logic. Negative plus positive. Give neutral. So now you have this is what we call resonance. If you localize the pi electron system, it turns a lone pair. Resonance is what will help you to understand the stability of molecules of organic compounds. Like it enhances what we say, let's say it enhances stability. Are you okay with that? It enhances stability of organic compound. So that when you are doing your mechanism of reaction, you know what is more stable than which one is more stable, which one is not stable, and so on and so forth. So before you can do this and all that, you have to know how to write level structure. I think this one you should know this before, but formal chart can be a little bit strange, but I will explain both of them now. So when we say level structure, all organic compounds majorly are covalently bonded. Wait, we talked about this before. When we say covalently bonded, that means they share electron. For example, CH4 shares electron. This is how to write level structure. Okay, the electron here, this one of this, they join together so that you can have this. So that you can have this. Abby, this is the same thing. So they both share. So sorry about that. Actually, so you have you move this to this. That is how to write a level structure. So if you are doing level structure, so you have to know this. We have different ways to write structures in organic chemistry. We have we have the Lewis structure, or what we call the Cooley structure. We have bond line and angle formula. from not right chemical structure and organic compound. We have bond line and angle, bond line and angle, bond line and angle formula. We have condensed formula. Condensed formula. Now look, I want you to get something here. We have the condensed formula. This is Lewis structure, Kipling structure. Bond line and angle formula. These are the bond line and angle formula. At every point you have a carbon, carbon. These are okay now. That is bond line and angle formula. You can see a bond, a line, and angle. Is that okay now? So that is how to write structural formula in organic. So condensed formula is just like having this CH3, CH2, 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 CH3. Okay, that is a condensed formula. So that is formula for structural formula in organic compounds. So that is structural formula in organic compounds. So if you want to write resonance, you must follow Lewis structure of writing organic formula. So you must follow Lewis structure. Right, yeah. If you want to write the resonance structure, okay, you have to use Lewis resonance hybrid. So you have to use Lewis structure. So Lewis structure is what you are going to take note of. Is that okay now? So how do you do that? How to write Lewis structure? These are basic actually. First thing is you identify a central atom. What's the central atom? A central atom with the least molecularity. Now, what did I mean by that? For e.g., H2O, what is the central atom? O is the central atom. Are you okay with that? So you identify the central atom, alright? So the second one, so every other ones are other atoms. These are other atoms. So, but this is central atom. So the second point is identify their valency. The valency of electron, their valency or their valency, and also their charges. So if you identify valency, what's valency of oxygen? Oxygen valency or valence electron is what? 6. That of hydrogen is what? 1. So the charge is 2. So if it is positive, the amount of positive, let's say n positive. So let me say plus 2, lower charge okay. So that means you are going to write 2. Is that okay now? So if minus 2, it's going to be minus 2. It's going to be 2. So now if you want to do your Lewis structure, you put the central atom down. So after you've done this, all right, so that means you have what we call, then you now do this calculation. Okay, oxygen atom is 6. How many oxygen do we have? We just only have 1, abi. So hydrogen atom is how many? 2 of hydrogen. That will be 2 times 1. Are you okay with that? So to calculate total electrons. Is that okay? So now any charge, if it is, let's say we have positive charge lower, okay, you are going to minus from it. Is that okay now? To negative charge lower, okay, you are going to add the electron to it. So that means it has gained extra 2 electron. Are you okay with that? Are you okay with that? So for this one, it doesn't have any charge on it. So that means you have 6, 2. Total electron will be what? 8. So that means the electron you have in the whole of the system is going to be what? 8 electrons. So if that should be the case, then if you say put the central atom at the middle, which is oxygen. So I'm just using it, like I'm making it big so that you can see. Put the other atoms around it. What's the total electron on oxygen? Outermost electron 1, 2, 3, 4, 5, 6. Just spread it like that on it. So this one you have 1. So then connect the one that is we are talking about completing octet structure, abi? Octet or duplex structure. Whenever we are bonding, what is bond itself? It's just for them to attain duplex or octet structure. That is why we are doing all this bonding of it. So you have this already. So that means we have this and this. Are you okay with that? Are you okay with that? So that is the. So you can now say how many electrons do we have together? 1, 2, 3, 4, 5, 6, 7. So if it's more than this, that means you are wrong with your structure. So you can now say the structure of water is just this. Okay. But now look at this. Actually, the structure of water is not always straight like this. Why? There is something we call SEPA. SEPA's rule. That's how to write electron. SEPA's rule states that valence electron pair repulsion. These are two lone pairs, alright? They will repulsing each other. So they have the same energy. Alright. Lone pair. What is I'm doing? Lone pair have higher energy than lone pair bond pair, which is more greater than bond pair. Is that okay now? Now this is a lone pair, they have higher energy, so they always want to stay at the same region. So when you have the structure, actually the two lone pair will come here, this one too will also come. They will compress down the other bond pair, these are bond pair, to the equatorial region. So because of the energy both of them has, they will make the shape of water to what? To be bent. That's why the shape of water is bent. They call it fish shape. So water is fish shape indeed. So on and so forth like that. So if you want to write Lewis structure, that's how to write Lewis structure. Are you okay with that? So for example now, you can do that for ammonia, do that as an example in your own. Lewis structure for ammonia, Lewis structure for NH4 plus, Lewis structure for CO2, Lewis structure for PbCl5, Lewis structure for CH3, CH2, CHO, and so on and so forth. Let's use an organic example as what we have there. Right, for organic example of what we've been doing. Now, if you look at this guy, carbon, alright. Majorly, we are talking about organic compound. Carbon and carbon will always come together. You have carbon here, we have carbon here, we have carbon here. Are you okay with that? But this O is directly connected to this one. So let's say we have 1, 2, 3, 4, 5, 6, 7. What is valence electron of? That is 4, 4. Abi now, they come together. So because O is directly on this, so we have O to this guy, Abi, and O we have how many electrons? 1, 2, 3, 4, 5, 6. Are you okay with that? It is going to have 6 electrons. All right. So here, how many hydrogen do we have around it? 1, 2, 3. On this carbon, how many hydrogen do we have? 1, 2. On this carbon, how many hydrogen do we have? We have 1. Abi. So let's now join the bonds together. This one come here. This one come here. This one come here. Alright, this one too come here. This one too join this. This one too. You can see that this one is here to be complete, so it can form bond with this. This one is here to go. This one is complete. So that means this and this. How many? 1, 2, 3, 4, 5, 8. 8 electron here. 8 electron here. This one is complete, but this one is not yet complete. It can form a bond. Sorry. We have this, Abi. So we have these two. So, but this one too is left with 2. So this one can come here, while this one too can come here. Are you okay with that? Is that clear now? So that the both of them can contain octet 1, 2, 3, 4, 5, 6, 7, 8. Now there is something they call expanded octet rule. Well, that one is not meant for you. Expanded octet. So there are some exceptions to valence bond electron, valence theory. Okay, perhaps expanded octet, like all those period 3 elements can expand their octet. For example, sulfur can have more than 8 electrons. Phosphorus, chlorine, and so on like that. So those guys can expand their octet structure. Phosphorus, sulfur, oxygen. Yeah, period 3. Just look for period 3 elements like that. So now here, that means we have C, H, to H, they be in the same region, to H. This one H, let's put the H down. This one too. Now for this one to be, so because of oxygen is greater, the lone pair will be here. So that means we have this. Abi, are you okay with that? So if you don't want to compress it, we make the bond to this side. So you have this. Now that is Lewis structure of this compound. Are you okay with that? So we'll use this one as an example later. That is Lewis structure of the compound here. Alright, fine. Since we know how to write Lewis structure, we know how to write Lewis structures, and that is fine. If we look at this guy here, he's carrying plus. Should I do that? NH4. Let's do NH4 plus. Why is it carrying plus? So that means we have nitrogen, we have hydrogen 4, we have this one. Nitrogen, what's the valence electron? Its atomic number is 7. Atomic number of nitrogen is 7. Abi? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen 7. So it's going to be 2,5. So the valence electron is 5 electrons. This one is times 4 electrons. Are you okay with that? Since we have plus, because of this plus, that will be because of positive 1. Okay. What did I say you do? That means you are going to do what? Minus 1 electron. Are you okay with that? So 9 minus 1, that will be 8 electron total. Are you okay with that? So now, what does that mean? That means you have this guy, spread the electron around it. Spread the electron. 5. So hydrogen here, hydrogen here, hydrogen here, and hydrogen here. Alright, so since we have star, this one complete, we have star, this one complete, we have star, this one complete, we have star. Now if you look at this, 1, 2, 3, 4, 5, 6, 7, 8, on nitrogen is already complete. But what is this extra? That means this guy here is going to donate 1 electron. So that's why the arrow is always like this. So if you don't want to write this, you say this guy has expanded this, is having this. Okay, are you okay with that? So that will be the structure actually. So you can now say this to this to this to this to this, then you bracket that plus. Are you okay with that? So that is how to write the Lewis structure of organic compound. If it's minus, you see it there. If it is plus, you see it there. Are you okay with that? So that is that. You can do that for SO2. You can do that for SO4 2 minus. The same thing, the same way. Yes, you do that for SO4 2 minus. Alright, so you have that. So that is just that. So now let's talk about formal charge. For example, when I do the movement of this other guy the other time, I do like this, Abi, and I said I move the arrow to this side. So I have this, Abi. So having this, I have this minus. Okay, 1 plus be by relay. Yes or no? Alright. This is resonance. Movement of pi electrons in the system. That is resonance. So why is this one carry plus? Why is this one carry minus? You see it now. So understanding formal charge. What is formal charge? Formal charge is in knowing where the localization of pi electron is. Formal charge is given by a formula which is, let's say Fc is equal to the valence electron minus bonding electron, that is alright, minus half into brackets non-bonding electron. Alright, we can say valence, that is valence electron, or the atomic group, or the group of the element. Valence electron is same as the group of a particular element, minus bonded electron minus half of lone pairs. Alright, so it will guide you to know why do you have this one carrying positive? Close of any positive load. Let's say you're having an organic compound. Sorry for using that. Anyway, so why is it having positive? Let's say, why is nitrogen carrying positive? Why is it that the positive is on nitrogen, not on hydrogen? Why? So nitrogen, as it ought to be, let's say the formal charge of nitrogen in this particular compound in NH4 plus. So it's going to be valence electron of nitrogen is what? 5 minus how many bonding electrons do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 8, Abi. Are you okay with that? Minus half, lone pair of electron. Okay. I'm coming. That should be an error. I'm coming. Let me finish this. Half into bonded lone pair. Oh, sorry. It should be lone pair. Sorry, that is an calculative error. Sorry, please let's do it here. So formal charge is given to be valence electron minus lone pair that is minus half bonded electron. So that will be the formula. So for example, for that of n of the n in NH4 plus, okay, so that will be valence electron is 5 minus lone pair is 0 minus half into brackets bonded electron is 8. If you calculate the bonded electron, you can see 1 2 3 4 5 6 7 8 abi, so that is 8. So that means it's going to be 5 minus 4, which is going to be plus 1. That is 1. IUK is positive 1. Tobacco is less than 1 might be minus or something. So let's now do that of formal charge of the CO, Tony double lone pair and minus. Sorry, that's this. And this one is plus. So the formal charge of carbon in this compound, carbon is 4 minus lone pair on carbon is 0 minus into bracket. How many bond pair do we have? 1 2 3 4 5 6. So half of 6. Are you okay with that? So that will be 4 minus 3, which is what? 1. Positive 1. Is that okay? That is why it's carrying plus. That is why this one is carrying plus. If they give you something like this and they ask you to put the charges on it, so that is where this thing comes in, okay? How do you know that it's going to be plus here? How do you know that it's going to be minus here? So for that of oxygen, you know oxygen is valence electron is 6, abi, minus lone pair. How many lone pair do we have? Oh, yeah. 8 1 2 3 4 5. Sorry. Okay. 1 2 3 4 5 6 minus 6. Okay. Minus half into bond pair. What is how many bond pair? 1 2 bond electron rather. That will be 6 minus 6 minus 1. So that will be 6 minus 7, which is what? Minus 1. So that's why it's carrying negative charge. Are you okay with that? Are you okay with that? So if we do, that's why it's carrying negative charge. So formal charge will guide you in order to know which one is going to carry positive and negative charge. So that is, then we now go to what we call resonance structure in full force. Let's go to next resonance structures in full force. All right, let's pause here before we move to resonance structure in full force.